Good morning, students. Am I audible? Hello? Am I audible, students? Okay. Let us wait for 5 minutes because only 6 participants have joined. We will wait for 5 minutes and we will start at 10:05 sharp. Okay. So almost 44 students, 45 students have joined. So we will start with the lecture. Just tell me whether the screen is visible to you. I'm sharing my PPTs. Okay. Whether the screen is visible? Okay. So let us start with the lecture. So in the previous lecture, we have seen what is the compiler and uh, what is the job of the compiler. So compiler basically is a language translator which converts the high level language into low level language. Along with this, it reports the error present in the source code. So the phases of a compiler, the process of compilation is divided into 6 phases rather. And main 2 phases of compiler design are analysis phase. So the analysis phase, it is the machine independent. That means it depends upon the source code, that is the language. So which language you are preferring, depending upon that language, the source code is getting converted into the intermediate code, and that is called as analysis phase. The analysis phase is again subdivided into 3 phases, which is the lexical, syntax, and semantic analysis. So 3 phases, which together will form the analysis phase. Then the second phase of compiler is the synthesis phase. Now the synthesis phase is actually the machine dependent phase, where we need to check the final code so that the target code is generated as maybe assembly language or low level language. So depending upon the machine language or assembly language, depending upon the machine, we are going to carry out the synthesis. So for synthesis of compilation, you have the intermediate code as the input, which is generated in the analysis phase. So we have total 2 phases. One is called as analysis phase. So in this analysis phase, you are providing the source code. Who is that? Roll number 71. Kindly check whether your mics are off or not. Okay, so the source code is provided as an input, which is the high level language, and you are going to pass it to the analysis phase where it is converting into the intermediate code. So this intermediate code is neither dependent upon the source language nor it is dependent upon the machine language. So it is an independent code. This intermediate code, which is the output of analysis phase, is further provided to the synthesis phase. And then after that synthesis phase, you are going to have the target code. So target code is nothing but the low level language. And that is how the compilation process works. So here the source language is converted into intermediate code. From intermediate code, it acts as an input to the synthesis phase and it is getting converted into the target language, which is the low level language. So that is the whole process. Out of that, again, we have seen the subdivision of analysis phase as lexical analysis, syntax analysis, and semantic analysis. So the further three subdivisions are like this. So you can see in the diagram. So it has lexical analyzer, syntax analyzer, and semantic analyzer. Out of that, we have seen the working of first three phases. So when source program is provided to the lexical analyzer, we have seen that the tokens are getting generated. So tokens are nothing but the lexemes which are grouped together to form tokens. So those tokens are generated in the lexical analyzer. Similarly, the errors which are available in the source code, they are also reported in the lexical analysis phase. So the tokens which are not fitting meaningfully correct, or they are not getting any token generated, such errors are reported in the lexical analyzer. Then second is syntax analyzer. So syntax analyzer is the second phase. So the tokens generated in the lexical analyzer is provided as an input to the syntax. So source program is provided to the lexical analyzer. It forms tokens. Those tokens are provided as an input to the syntax analyzer. And there we are going to get the parse tree. So I will write in short tree. So those tokens are arranged in a hierarchical manner to form a tree. That tree is also called as parse tree or syntax tree. So after analysis, after syntax analysis, you are going to get the parse tree. Now the evaluation of that parse tree is done. So once the tree is generated, then you are going to evaluate it in either top-down approach or in bottom-up approach. So always the operators are forming the nodes where the identifiers or variables are forming the leaf nodes. And the bottom-up approach is followed to evaluate the tree. Then after that, the semantic analyzer is present, and semantic analyzer accepts this syntax tree as an input, and it generates the again the tree only. It is available in the tree manner or the structure of tree only, but it is checking the meaning. So it has to do with the grammar and whether you are forming the meaningful statement or not, that is checked by the semantic analyzer. So grammatical and meaning related issues are handled in the semantic analyzer phase. Now all these three phases, you can see they are attached to the syntax table, or instead of syntax table, it is also known as symbol table in general. So here all these three phases are attached to the symbol table, where entries of tokens are made, the type of that token is getting saved, and the value for that token is also getting saved in the symbol table, so that those values related with the token are further used by the intermediate code generator, code optimizer, and final code generator. So every phase is dealing with symbol table management, because once the tokens are generated, they are getting stored here, and further whenever required by remaining phases, the tokens or the information about the tokens is taken out and used for the further process. So that is why the symbol table is attached with the all phases. Similarly, error handler is also attached to all the phases, so that every phase can report the error available in the code. So lexical analyzer will also report the lexical kind of errors. That means whenever the tokens are not forming. Whenever the tokens are not forming, then it reports such errors which are known as lexical errors. Similarly, the syntax analyzer detects the syntax errors. So it determines the syntax of the program. So it checks according to the source language, the proper syntax has been followed or not. So if that uh, syntax is not followed, then it reports the error to the error handler routine, which are called as syntax errors. Similarly, if the tokens are not connected meaningfully, if they are not giving any meaning with respect to the grammar, then semantic errors are also generated, and that are also given to the error handler subroutine. So all these three phases we have seen in the previous lecture, and now we are going to see the next phase, that is called as synthesis. So in the analysis phase, first is lexical, second is syntax, and third is semantic. So the analysis phase is complete, and now the intermediate code is generated, which is in the form of tree structure, and that is provided to the intermediate code generator, and which will give you the language which is independent of source as well as target program. So now let us go to the second phase of the compilation process, which is called as synthesis. Okay, so is there any difficulty up to this, students? So this is the portion that we have revised, that we have seen in the previous lecture, the three phases and their working. So we have revised the three phases, and now we are going to start with the intermediate code generation. Is there any difficulty? Okay. So lexical analysis, token is getting generated, and the token name and the attribute value is getting stored in the symbol table. Syntax analysis, the tree structure is getting generated, where the nodes represent the operator and child represent the variables. The semantic analysis, it is mainly used for type checking or grammatical kind of errors, and it checks whether the tokens are giving you the proper meaning to the it is giving the proper meaning to the syntax or not. So that is nothing but the semantic analysis. So type checking and all these things are carried out here in the semantic analysis. And then we are going to start with the intermediate code generation. Okay. So this is the phase number 4, intermediate code generation. After syntax and semantic analysis of the source program, many compilers generate explicit low-level or machine-like intermediate representation. Okay, so here we are going to get the intermediate code. Here we are going to get the intermediate code, which is actually the low level kind of language, or it is machine level language, or it can be assembly language also. So this intermediate representation should have two important properties. So whenever we are going to generate this intermediate code, it should follow these two characteristics. First is it should be easy to produce. That means this intermediate code should be easy to produce, and it should be easy to translate into target machine. That means it should be compatible with the source. That means from source to intermediate code, easy generation should be there. And from intermediate code to target language, again the easy translation should be there. So source to intermediate code, the process should be easy. And again, intermediate code to target level also, the translation should be easy. The considered intermediate form is called as 3-address code. So why it is called as 3-address code? Because it is holding the 3 addresses on each line. So it has 3 addresses on each line, and that's why it is called as 3-address code, which consists of a sequence of assembly-like instructions with 3 operands per instruction. So it has 3 operands per instruction. So on every line, you have 3 addresses, or we can say it as 3 operands. Each operand can act like a register. So it is the choice of the programmer that whether programmer wants to store the operand in register or in a memory address. So every time the 3 operands are there in every instruction, and it is stored like a register. This phase bridges the analysis and synthesis phases of translation. So it is the bridge between the analysis phase and synthesis phase, because this intermediate code is getting generated, which is neither dependent upon the source. What analysis phase is telling you? Analysis phase is dependent upon the source, and synthesis phase is dependent upon the machine. So the analysis phase is dependent upon the high level language, which is a source program, which is the language dependent phase, and synthesis phase is the machine dependent phase. And this intermediate code is acting as a bridge between the two. So this intermediate code is neither dependent upon the machine, it is not dependent upon the source code. Okay, so in earlier example, we have seen that we have generated a parse tree. We have taken the example A equal to B plus C into something. C into 10 something. Okay, this was our example. So 10.0. This was our example. So earlier, the input string given was A equal to B plus C into 10.0. The bottom-up approach is followed. That's why C into 10 is carried out first. Then here the type changing is taking place. That is, the type of this is real or float. So I will convert it into float to integer, so that the multiplication will take place and it is ultimately getting stored in the integer variable. So this type conversion is carried out in the semantic phase, because we know that semantic is acting as a type checker. So it is checking the type of the variable and perform the modifications if required. So here is the tree. This tree is provided as an input to the intermediate code generation phase. So this is the semantic tree getting generated in this phase number 3, and it is given as an input to the phase number 4. Now, after performing this intermediate code generation, what will be the output? So the output is nothing but you are going to get the 3 address code. So 3 address code. So for that, the another function or another property of the intermediate code is the 2 properties we have seen. First property is it should be easy to produce and it should be easy to translate. The third property is it is making use of temporary variables. The intermediate code always makes use of temporary variables. So I will have the first temporary variable T1 because that temporary variable I will be using to carry out one operation at a time. Because if I am dealing with one operation, roll number B36, kindly mute yourself. So here the temporary variables are used because at a time we are going to carry out one operation only. So here is the temporary variable T1 in which I am carrying out this type changing operation. So float to integer, this operation is carried out here, which will convert this 10.0 into 10. So that ultimately I will be storing 10 in the T1. Okay, now on this line you are finding how many addresses. This is the value stored as a constant, or it can be also available in the register. So you can convert that value into integer and then you are going to store it in the T1. So on this line, you are going to handle 2 addresses only, the address of 10 where the 10 value is stored and the T1's address where we have to store the result after this conversion. Okay, so that is okay. Okay, even though I have got one message that maximize the screen, but even though I'm maximizing, is there any change you are observing in your screen? Okay, let me share my screen again. Yes, I have started the slideshow only, but I should share the screen, then it will be visible, I think. Yes, now it is okay?
Yes, ma'am.
Okay, so see here, so in the intermediate code, whatever the input is provided, that is the syntax or semantic tree, we can say. After semantic tree, we are going to get this intermediate code by making use of temporary variables. So in the earlier example, I will be doing first, I will be using the temporary variables T1, and in that T1 I am storing the float to int value. So float to int 10.0, this I am going to store it in the 10.0. This I am going to store it in the T1. Okay, so this 10.0 I will be storing it into T1. Here I am having only 2 addresses. right? Then why the name is given as 3 address code? Why the name is given as 3 address code? Because what it is saying that every instruction with 3 operands per instruction. So this is one instruction, but it is holding only 2 addresses. So 3 address code is nothing but it has maximum 3 addresses per instruction. That is the meaning of 3 address code. So maximum 3 addresses should be there. More than 3 addresses, it is not possible. So it is called as 3 address code. So less than 3 is allowed. So here I am handling only 2 addresses. One is where the value 10 is stored, and other is the T1 is wherever it is stored. So that is called as your first instruction. Then once you get this value in T1, the next step is you have to perform the multiplication. I have to perform the multiplication of, I will draw the tree here for your understanding. So A equal to B plus C into 10. Okay, so it is a expression you are having, and that is converted into so that is converted into now 3 address code. So first operation I have done, that is converting this float number to integer. So float to integer conversion is done, and that is stored in the T1. The next operation is perform the multiplication. So you have to carry out the multiplication. After this multiplication is done, that result is stored in some other temporary variable. So I will use T2. So every time, remember, in every step you are going to make use of temporary variable. That is the characteristics of 3 address code. So T2 will have the multiplication of C with T1, because the earlier result after conversion, type conversion, is stored in the T1. So now I will carry out C into T1. So once this is done, now you can check how many addresses are there. Address where C is stored, address where T1 is stored, and address where T2 is stored. So total you are handling 3 addresses with 1 instructions. The next is, after performing this multiplication, you have to add this result into B. So the result is available in T2. The result of multiplication is available in T2. So I will write here also, this is your T1 now. At this stage, you are getting your T2 value, result of this operation. And then this T2 plus B you have to do in order to get the next result, T3. So again, I am using some temporary variable T3, which will perform the addition operation, or which will have the addition result of B plus earlier result T2. So this T2 is added into B. Now also I am handling 3 addresses. So you can see in every step, maximum 3 addresses are handled. Okay, 2 or 3. You can have less, but maximum value is 3. That's why the name is given as 3 address code. And after that, you have to assign that result. You have to assign this T3 value to A. So the final step is A equal to T3. Okay, so what I have done now, the source code, which was there in maybe C language. Suppose source code is in the C language. And what was the source code? A equal to B plus C into 10.0. This source code was present. But now I have converted it into 3 address code where every instruction deals with maximum 3 addresses, and it is neither dependent upon the source code nor it is dependent upon the target code. So you can observe neither it is the assembly language nor it is a binary language of 0 and 1. Okay, but it is the intermediate form, which is neither a source language, it is nor the target language. Okay, all of you are getting up to this. So here also I am handling only 2 addresses, the address of A and the address of T3. Okay, is it clear? Okay, so this is the phase 4 where the intermediate code is getting generated. Now after this, you have this code with you. So what is the next phase? Next phase is called as optimization. Code optimization. So phase number 5 is called as code optimization. Now, the code optimization can take place at phase number 5, or it can also take place at phase number 6 also. So you can have the interchange between 5 and 6. You can have interchange between 5 and 6. So here the code optimization, suppose we are observing the optimization of code at phase number 5. So let us see what is the meaning of code optimization. So what do you understand with the name itself? Code optimization. So optimization is something which is equivalent to reduction. So whatever the code is generated in the earlier phase, that is the 3 address code. So whatever this 3 address code is generated, that we can reduce. That we can reduce in this phase. So why there is need of reduction? So the time required may be the concern, because handling 4 instructions will take larger amount of time. If I minimize it to 2 instructions, then obviously the time required will be less. So that can be one option, or second option can be the memory management. If the memory required to perform all those 4 operations is more, then after optimization, I can reduce that memory requirement. So in 2 ways it may work. That is the time required to implement the code or execute the code, or the memory required to implement this code. So in both ways, the optimization can be achieved. But whether optimization means simply cutting out these statements, directly I am deleting this 3rd number line and 4th number line. Whether this is the proper optimization, instead of 4-line code, I have made it 2 lines. But whether I will get the same output as per my desired output? No. If I am directly deleting the statements, it will definitely change your target code. In turn, you are not going to get your desired output. If I am changing this code, then I will not be getting my desired output. So the optimization is carried out, but without changing the meaning of the program, or without changing the final output, desired output. Okay, so let us see what is the code optimization. So the compiler looks at a large segment of program to decide how to improve performance. So this is only the one instruction, A equal to B plus C into D. But for this one instruction, we are getting 4 lines of code. So such 100 instructions are there, then 100 into 4, 400 lines of code in the intermediate language I will be generating. So that is very time consuming. So the computer always require the improved performance, and that is the job of the compiler or code optimization phase, which will perform the improvement in the code. So let us see. The compiler looks at large segments. So large segments we have seen already. What is the large segment of program? To decide how to improve the performance. So through code optimization, we are able to improve our performance. The machine independent code optimization phase attempt to improve the intermediate code so that the better target code will be achieved as a result. So this is the intermediate code which is not dependent upon the machine. So this code is used for the optimization, because once we are going to get the target code which is machine dependent, then further optimization becomes difficult. So we need such a code which is neither dependent upon machine nor dependent upon the source, and on which we can perform the optimization. Okay, so the code optimization is done on the intermediate code. Usually better means, what is the meaning of better? That is how you are going to get the better performance or improve the performance. So that better means either faster, we have seen in terms of time, it should give you faster execution, or in terms of shorter code, that is memory requirement. So in order to store less amount of code, so you should get the shorter code, or target code that consumes less power. Sorry. So the third condition is target code that consumes less power. What is the meaning of this? Consider the example. If I have the instruction like b is equal to a raised to 3. Okay. So the instruction is what? B equal to a raised to 3. Now I have to convert this into the intermediate code. So for that, I should use the power of operation, right? So power of function, in which power of function is done with a and 3. So it is nothing but power of function with a as a operand and 3 as a power. And this result I will be storing it in B. So this instruction where I am using the power of operation is using the high power. Roll number B30, kindly mute yourself. So here it is making use of high power, or we can say in other words that it is costly instruction. The cost for using the instruction power is a costly one. Instead of that, what we can do is we can perform the same operation by carrying out the multiplication. If I'm writing this a dot a dot a, what is the meaning of it? It is similar to a cube. So what I am doing, I am replacing the power operation by the multiplication, which is consuming less cost or less power as compared to this. Similar way, if I am having b equal to 2a, suppose, so this is the multiplication between 2 and a. This can be changed as b equal to a plus a. Whether I am changing the meaning, 2a is nothing but a plus a. I am not changing the meaning, but then also this costlier instruction is converted into cheaper one, so that ultimately it consumes less power or less cost. So such techniques we are going to use in the optimization. Okay, so there are simple optimizations that significantly significantly improving target program without slowing down the compilation much. So we have to apply the optimizations which will significantly improve the time. So we have already seen in terms of time, in terms of memory, and in terms of power or cost, the code should be efficient one. The optimization cannot make inefficient algorithm efficient. What is the meaning of it? If already the algorithm is inefficient, then the compiler will not change that algorithm. It only optimizes that, but ultimately the output is, or it is not giving you the proper output because it is already inefficient. So it only makes the efficient algorithm more efficient. So this is the efficient output, efficient algorithm or efficient steps, which is giving me the required output, A equal to B plus C into 10.0. So with these steps, I can perform the optimization and I will get the better output than this. But if the algorithm itself is not giving you proper output, then with optimization, you cannot expect that it will give you the proper output. So inefficient algorithm do not become efficient with optimization, but efficient code becomes more efficient. That is the job of code optimization. Okay, so here let us reduce this code now. So how to reduce? So for that, I can perform the two reductions. First is here, I can, instead of storing this result in T1, I can directly multiply it with F2I 10.0. So that is my first step. So how it is achieved? I will do like this. So T1 is equal to C into F to I, that is float to integer 10.0. If I will do this, these two steps I have merged together. This is the step number 1 and this is step number 2. So I have merged these two steps together. So converting float to integer 10.0, storing it in some temporary variable and again using it for multiplication purpose. Instead of doing this, I am doing like this operation, and ultimately 2 lines of code is converted into 1 line, but remember, without changing the meaning of the code. We have not changed the operation. Ultimately, I am going to get C into F, C into 10.0 only. So here I have reduced this T1 and T2, and this step I have done, or I have stored as T1 here. Okay, so reduction in the memory locations. The required memory locations for storing the temporary value were 2 earlierly, T1 and T2. Now I require only one temporary variable, that is called as T1. Okay, so that is your first optimization without meaning change. The second optimization is here. You can see result of B plus T2 is stored in the T3. And again, T3 is assigned to A. So instead of doing this, I can directly assign the result of B plus T1 here, because T2 is replaced by T1 here. So T1 plus B, this result, instead of storing it in T3, I can directly assign it to A. So that gives me again reduction of 2 lines into 1. So what I am doing, ultimately I am making use of only one temporary variable T1. Earlier I have T1, T2, T3. But now with this optimized code, I am using only one temporary variable. So in terms of memory also it is efficient. In terms of size of the program also it is efficient. That is, shorter code is also achieved. Instead of 4 lines of code, I am achieving here 2 lines. And instead of 4 lines, I am achieving here 2 lines. And in terms of memory also, instead of having 3 temporary variables, I am making use of only 1. So it improves the execution time, it improves the memory requirement. So ultimately, I am getting the optimized code. All of you are getting up to this? Yes?
Yes, ma'am.
Okay. So the code is getting optimized here. So always remember, the meaning is not changing, but we are getting the efficient one. That is your phase number 5. And as soon as phase number 5 is over, the next is phase number 6. So this code is given as an input to phase number 6, which is called as final code generation. So let us see what happens in the final code generation. So next phase is final code generation. That is phase number 6. So it is the last phase of the translation. It takes input, intermediate representation of a source program, and maps it into the target language. So this takes the 3 address code or intermediate representation, which is optimized code now. So it takes this as an input and it generates the target language. If the target language is machine, code, register, or memory locations are selected, or we can say that the language is machine level language or assembly language, then we are going to select the code accordingly, the number of registers and memory locations for each variable used in the program. So we are going to store every variable in maybe registers or memory locations. So we are having this 2 lines as an input, and we will convert it into assembly language. Then the intermediate instructions are translated into sequence of the machine instruction that perform the same task. So these instructions are translated into assembly language, and which is carrying out the same task, but which is understood by the machine now. A crucial aspect of code generation is the decision assignment of register to hold the variables. So how to generate the good final code? So it depends upon the assignment of register to hold the variables. So how efficiently we are handling the register, it will decide the good final code, that is good target code. So efficient handling of register, that is assignment of the variables to the register. This assignment should be handled efficiently to get good target code as output. So what will be the target code for this? So I will have the target code like I will be using the machine assembly language. So move instruction I will be using. First, I have to move this 10.0, or if I'm going to multiply as a constant, then it is okay. So first I will move this C. So I will move the C value into some register R0, let us assume. I will be moving the C in some register R0, then perform the multiplication with 10.0. So I will be performing the multiplication. So MUL multiplying the R0 with 10, multiplying the R0 with 10 because float to integer 10 value. So integer 10 is taken. After this multiplication, the result is available in the R0. So you have to use this R0 and add it into the B. So for that, first I have to move the value B in some R1 register, and then I will perform the add operation. So add operation is carried out between R0 and R1 because R0 is holding the multiplication result and R1 is holding the value of B. So I will carry out addition of R0, R1. Always remember this is your destination. That's why the result will get stored in the R0. And after that, you have to move that result R0 into A because you have to assign it to the value A. So this is your assembly language code, which is getting generated in the code generation. So this is called as efficient use of register. Why? Because this 10 is a constant number, so I can directly multiply a constant value with the register contents. So that is nothing but instead of assigning a separate register to store this 10 value, now I am using only R0 and R1. Otherwise, what will happen? To store this C, I am using R0. To store 10 value, I am using R1. To store B value, I am using some R2 register, and so on. So I should use the assignment of register properly so that the final code generation is a good quality code. Okay, all of you are getting up to this?
Yes, ma'am.
Okay, boys side. Boy students. Okay. So I assume you are getting as no doubts are there. Okay. So this is how the compilation process is carried out through various phases. So in the next phase, here is the source program. The scanner is the first phase, which is called as lexical analysis. It generates token given to the parser. So parser perform parsing, a tree is generated. Then the code generation, that is intermediate code generation, is done. And then the intermediate code generation semantically checks and perform the final code generation. And then also you can apply the optimization. So here also on this, you can apply the optimization, but it is easier to apply it on the intermediate code instead of the target code, because you have to take care about the syntax of the machine language. So move, multiplication, all those things you have to consider while optimizing the code. And that's why easier method to optimize the code is at this level for intermediate code. So once you are going to optimize the code, then the object file is getting generated. So this object file is acting as your target program, where the input is provided to this object file and output is received. So next is symbol table management. So we have already discussed the symbol table is a data structure containing a record for each variable name with fields for the attribute of the name. So once a token is generated, they get stored in the symbol table. So for every name or every variable, the entry is made in the symbol table. The data structure should be designed to allow the compiler to find the record for each name quickly and to store or retrieve the data from the record quickly. So symbol table can be stored in multiple data structures. Like you can use the different data structures like maybe linked list, arrays and all. But the data structure should be designed in such a way that the retrieval and storage should become easy or quick. So we can say that the data structure should be designed so that for every entry, the store and retrieval of the data should be quick. Okay, so that is the only requirement for symbol table management, that easy storage or quick storage and quick retrieval for the next phases. These attributes may provide information about the storage allocation for a name, its type. So what are the different fields in the symbol table? It is explained over here. That is, the variable name is the first entry, its data type is the second entry, its scope. Scope means within the program for how much time it is used. So here I am using the variable ABC from start of the program to the end of the program. So scope of these variables ABC, they are lifetime, that is lifetime of that procedure. So it is nothing but the scope. And in case of procedure names, such things as the number and type of its arguments. So if any procedure call is there, function call is there, then you should define the number of arguments passed to that function and the type of that arguments. The method of passing each argument. So how we are passing the variables to the function, may be called by value or called by reference. So all these things are taken care. Then comes the error handler routine. So as we have discussed earlier, error handler routine is attached with all 6 phases, same as that of symbol table. Symbol table is also attached to all the phases. So here also error handler routine is attached to all phases, where the errors are getting detected from the source program. The error message should allow the programmer to determine exactly where the error has occurred. So if you have seen the C compiler, Turbo C, so you are finding the line number, right, where the error is occurring, semicolon is missing. If you are getting that error, then you are knowing at which line. The line number is also specified by the compiler. In the same way, the error handler routine also should explain the programmer, or it should allow the programmer to determine where the error is occurring. Error may occur in all of the phases of a compiler. So error can occur in all phases. So in every 6 phases, the error is possible. Whenever a phase of compiler discovers an error, it must report the error to the error handler. So we have seen that structure of the program. We have seen the structure of this already, that whenever any error is encountered, that should be reported to the error subroutine, error handler. That's why it is attached to all the phases. Okay, so whenever the phase of compiler discovers error, it must report the error to the error handler, which issues an appropriate diagnostic message. So it is the job of the error handler to generate the message for that error. Both of table management and error handling routines interact with all phases of the compiler. So we have already seen this diagram, that symbol table and error handler are already associated with every phase of the compiler. So this is the whole process of the compilation. So here is the example. The symbol table. Position is equal to initial plus rate into 60 is the example taken. So this is the line. It is a line input source program. It is given to the lexical analyzer where the tokens are getting generated, where the first token is identifier. So ID represents the identifier. The first token is position. So in the symbol table, the entry is made at first location. The name of the variable is position. The type of the variable may be float or anything. In that way, the entries are made. Similarly, the second token is encountered, that is equal to sign, which is assignment operator. Then the third token is again identifier number 2. So in the second number identifier, you will find this initial. Then this plus is acting as one token, which is the operator. Rate is acting as a third identifier. So at 3 number identifier in the symbol table, you have this entry of variable rate. And multiplication is acting as operator and 60 is acting as a constant. So after syntax tree, you are getting the tree generated. After semantic, the type conversion is done. After semantic, you have intermediate code. So in the intermediate code, this tree is converted into 3 address code where each line has maximum 3 addresses to handle. Then comes the code optimizer where it is reduced to the number of lines of code. And then code generator is there, which will perform the generation of the assembly code or machine level language. And every phase is attached with this so that the value of the position will be changed here in every phase. So whenever your value of position is changed in the every phase, it is getting reflected back in the symbol table. So this is how the compilation process works. Getting it, all of you?
Yes, ma'am.
Okay. So this chapter is very small. Actually, only 3 bits are there. Out of that, 2 bits we have covered. This is the last bit, compiler construction tools. So we will see it in the next lecture. So in the next lecture, we will be finishing with our chapter number 1. Okay. So you can put your attendance in the chat box only once. Put your attendance in the chat box and make sure that you are writing only once. So we will stop here for today. And once you write the attendance, you may leave. Roll number A33 is there?
Yes, ma'am.
Okay. Roll number A68.
I wrote in chat box, ma'am. A33.
Yes, yes. Randomly, I was checking whether you are attending or just making the login and going anywhere. Okay. Roll number 68 is there. B division 77 roll number.
Yes, ma'am.
Okay. So if you have written your attendance, all of you may leave. I will also stop. Thank you.
किती जोडले